In this lecture, we will be learning the closure properties for both CFLs as well as DCFLs. I hope you know what is a closure property, and also we have seen for various set of languages like finite languages, infinite languages as well as regular languages. Okay, before starting the closure properties for both CFLs and DCFLs, let's see where we stand. We are at this point. Before this, we have learned the regular languages, here expressions and finite automata, also how to identify the regulars and non-regulars, and here the closure properties of regular languages. And also we have seen a special topic, grammars, regular grammars and context-free grammars. Now before this, we have seen how to construct the PDA and also how to identify the CFLs and DCFLs. So let's begin the closure properties of CFLs as well as DCFLs. Okay. Here, what do you mean by the closure properties of DCFLs? Right. We have the domain. Here we have the deterministic context-free languages. Assume each dot is one language. How many languages are there here? Infinite DCFLs, right? So this is nothing but the set of or domain. You have deterministic context-free languages in which you have DCFL1, DCFL2, DCFL3, DCFL4 and so on. There are infinite number of deterministic context-free languages present in this domain. Okay, what is the closure property here? Here closure property is nothing but an operation. So we take certain operations like union, intersection, various operations we are going to take, but among them few closure properties I am just discussing here, like intersection, complement. What else we have? Reversal and set difference, also language difference, simply you call difference, and concatenation. What else we have? Lot of the operations. Each closure property is going to be applied or going to be understood for this domain. Not only for this domain, we will also see for the context-free languages. Right. So when we are going to talk about context-free languages, here the domain is different, in which you will be seeing the all context-free languages, set of all context-free languages over the sigma. Here you will see context-free language 1, context-free language 2, here every DCFL also comes inside, right? C5 and so on. How many CFLs are there? Again, infinite number of context-free languages present over any sigma. So here the domain is different compared to the previous one. Previous one is all DCFLs and this domain is all CFLs. Again, we are going to apply various closure properties, like I said, union, intersection, complement, reversal, set difference and concatenation and so on. We're going to learn, is this union closed for this domain? You know what do you mean by closed? I hope you remember that, but let me tell you, there are two things will be given. One is given domain, like all CFLs or all DCFLs are given. Another one is given to you operation. Let's say a domain is, let's say A is the domain name, like set of all CFLs or set of all DCFLs or set of all regulars, the domain is given to you. Operation is a particular operation, let me say it is the circle, that's operation, right? Domain is given, operation is given. If anybody says A is closed under the circle, let's say A is closed under this operation called as circle. When we say this, it means simply we are saying A comma circle is closed. We can also write this way. When we say this, we say every two languages or every two elements in this domain. That means for all, let's say L1 comma L2 belongs to A. Any two languages you take. This is, let's say this is a binary operation. You know, sometimes you will be also having unary operation, then take only one operand. Here I am assuming binary operation, but also you can apply for unary operation or any array operation. Assuming that it's a binary operation, you need to take two operands or two elements from the domain. Then I have taken two languages from the set, and I'm going to apply such that if you are going to apply the operation like L1, L2, then this must be belongs to A. If this happens, then we say that operation is closed for the domain A. So it's very important. When you apply for mathematics, it would be very easy for you, like addition. If A is the natural set and that operation is the plus, then we can say that plus is closed for natural set, because you take any two natural numbers, do the addition, you will get again natural number. So it's very simple to say that take any two natural numbers from the domain, from the natural set, and apply the addition, you will get again natural number. So the same way, take any two languages from the domain, apply the operation. If you get in the same domain, if the result is in the same domain, then only we say it is closed. Otherwise, in case if you don't say all for all, another case, that is A is not closed under circle, then situation is different. Under operation, binary operation I'm talking about, then this is happening, right? If and only if there exist L1 and L2 may be same or may be different, you do not know, right? That depends on the example. L1, L2 belongs to A such that L1, when you apply with L2 the same operation, that is not belongs to A. That's enough to say it is not closed. At least one example you found in the domain, the languages are from the domain, but after applying the operation, result is outside the domain, then we can say it is not closed. Okay, so let's start this closure properties now, and we already know the closure properties for various other domains. But now the domains are very clear, depends on the question, domain is going to change. If I am talking about only DCFLs, now don't worry about CFLs and other domains. Okay, focus on all DCFLs. Okay, let's start. The first question is, let L1 and L2 be two DCFLs. So you have two deterministic context languages. Remember, I did not disclose what DCFL I am talking about. That means I am going to talk about any two DCFLs of the domain. Remember that. Okay. Then what is the union of two DCFLs? Simply I am asking, is that union closed or not for the DCFLs? Instead of asking the theoretical line, I just framed in simple sentence like let L1 and L2 be two DCFLs. Then what is L1 union L2? And sigma is given. Okay, sigma is for A comma B. Okay, so what is this L1 union L2? It means what is DCFL? L1 is DCFL, right? So DCFL1 union DCFL2. That's it. What is it? Over sigma A comma B. Think about two DCFLs. Is it always DCFL? It could be two answers, right? Either it may be DCFL or may not be DCFL. Okay, sometimes never be DCFL. Okay, depends on the domains. So here we will think about two possibilities. Is it always DCFL? If it is always DCFL, there should be an algorithm to prove it. So only sometimes DCFL, sometimes not, then you need an example. Why? Do you have any answer which goes outside the domain? Fix now your domain is all DCFLs. I pick from this DCFLs class the result. If it is inside always, then you have to prove using algorithm. Sometimes it is going outside the domain. Find which example that goes outside the domain. Okay, now the answer is, now you need to find, I know that the union of two DCFLs need not be DCFL. What is the right answer? Need not be DCFL. It means you should find counter examples. If I want to take, let's say, a power n, b power n, union, again I will take the same. What happens? Same happens, right? But we don't worry about this example. It's a trivial example, right? Proving, sorry. Proving DCFL is not difficult. Your problem is, do you have any example which is not a DCFL after doing the union of two DCFLs? So this we don't worry at all. Okay? We will worry about this is DCFL, right? This is DCFL. Of course, 2 is also same as 1, and this is also DCFL. 3 is also same as 1, right? All the 3 are same. We will worry about some two languages, let's say a power n, b power n, union a power n, b power 2n. When you take these two languages, if you do the union, what do you get? Do you get a DCFL? No, you don't get a DCFL. Then that's the reason you get, what do you get result? You get something like a power I, b power j. Here the strings are I is equal to j, or here the strings are that j is equal to, this is twice to the first one, right? So j is equal to 2 times of I. So here j is equal to twice to the I. So it's going to happen. Now whatever this is, it's definitely not DCFL. But what is it? It's always CFL. What is it? Always CFL. Indirectly, by combining these two statements, what you can say, sometimes DCFL, sometimes not DCFL, but whether it is DCFL or not DCFL, always answer CFL. See, how did you get the conclusion? So we know the answer is need not be DCFL. Need not be DCFL. That's true. But it's guaranteed always CFL. Because CFL, we have an algorithm with the help of context-free grammars. You can make a context-free grammar, you can make a context-free grammar, you can combine these two grammars with the help of star symbols of the grammar. Okay, that's why this as a proof for the CFLs. Any of CFLs we'll talk about it soon. Now answer is always CFL, so you can blindly choose option C, but B and A not guaranteed all the time. Okay, so union of two DCFLs is always CFL. When you want to talk about DCFL, need not be DCFL, or may be DCFL, may not be DCFL. Fine. This is the first question. You have to look at the union of two DCFLs, what happens. And you have a homework for that. You take that as homework, like union of two languages is DCFL. Then what is L1 and what is L2? Do you have any restriction for L1 and L2? The question I am repeating again. L1 union L2 is DCFL. I am not saying L1, L2 are DCFL. L1 union L2. If L1 union L2 is DCFL, then what is L1? Of course, same answer goes to what is L2. Fine. Let's move to the next question. If you want, you can take it as homework. That is 1. If L1 union L2 is a DCFL, then what is L1? One question you answer it. If you know what is L1, what is L2 also same. Okay. Is L1 always DCFL, or is L1 always CFL, or is L1 could happen anything. Okay. So think about what is L1. Second question. Let L1 and L2 be two CFLs. Then what happens union of two CFLs, like CFL1 union CFL2 is dash. Okay. Like finite union finite is a finite. Infinite union infinite is infinite. Regular union regular is regular. But DCFL union DCFL, we have seen, need not be DCFL. CFL union CFL, again it's CFL. It's very interesting, the union operation. Except DCFL, so far it's closed for all the domains so far, right? Except DCFL's class. Then here, how people can prove it? Take any CFL. I don't need to say this way, right? I don't take examples here. What I can take, I'll take a grammar, like I'll take a context-free grammar for this with S1 as a start symbol, with S1 as a start. Here for CFL2, I can write one more grammar for this, CFG2, which has S2 as start symbol. Then you want to prove that there is a context-free grammar, the union. That means if you want to perform this union, what you can do, you can write a new grammar. What grammar you can write? That is S arrow S1 or S2, and you keep the grammar of CFG1, CFG2 just below this. You keep the CFG1, copy it, and CFG2 copy it. So this is going to be new grammar. This grammar definitely generates this context-free language, no doubt about it, the result. Okay, so I can do union of two CFLs, you will get always CFL without any doubt. The problem is, if these two are DCFLs, you may not guarantee DCFL. I have shown an example why sometimes you may get which is not a DCFL, because of that multiple conditions you need to check. Okay, so what is the answer? A regular no guarantee, DCFL no guarantee, but always CFL. That union of two DCFLs also DCFL, union of two CFLs is also CFL. Okay, but when it comes to example, you should answer properly and correctly. Example, somebody given something like this: L1 is equal to A power n B power n, L2 somebody else is given A power 2n B power 2n such that n greater than or equal to 0. L1 L2 are given to you. When you perform L1 union L2, L1 union L2, what happens? L1 union L2, this A power n B power n union, you get A power 2n B power 2n, which is equal to, see, all these strings are already covered here, so you get A power n B power n, right? A power n B power n. It is DCFL. What is it? It is DCFL. So I told just now, union of two DCFLs need not be DCFL. That means sometimes you can get a DCFL. Sometimes when they have given example, don't say need not be DCFL. Answer you have to clearly show it is DCFL only. We know union of DCFLs may or may not be DCFL, but when the example is given, you should know exactly is it regular or finite or infinite, DCFL or CFL. You should answer it correctly. It might happen union of two DCFL might be finite language, because every finite is DCFL. I might be doing finite and infinite sometimes. In that case, you should answer properly. So look at the options and answer it accordingly. But remember general statements, how you are going to conclude. Based on all the examples, you are going to give the answer. But when the example is given, don't depend on the general. Okay, general is required when you have the strict answer. Okay, we'll see that too. Next, L1 is DCFL. What? And second, L2 is CFL. Then what you are trying to do here? Union of what? DCFL and CFL. This is what you are doing. What happens for this? DCFL union CFL. Okay, you are trying to do the union of two languages which are not there in the same domain. Okay, you may assume that. So DCFL in the DCFLs. So this is somewhat different. You may take any DCFL, you may take any CFL. Okay, so it's very important how you are applying it. I'm not considering my domain is only DCFLs. I'm not considering my domain is only CFLs. Here one operand is from the domain of DCFLs, another operand is from the CFLs. So this is given to you. Now you have to think, is it always DCFL? Is it always CFL? Is it always not DCFL? Is it always not CFL? Or it is sometimes DCFL or it is sometimes CFL? You have to focus on all. But let's focus on, is it always DCFL? Already you know DCFL union DCFL, no guarantee of DCFL. You already know that. So here focus is on CFLs. DCFL union CFL it is going to be always CFL. Why is that? You have a proof for DCFL you can write a context free grammar, and this CFL you can write a context free grammar. You can do the union, you can get always that is CFL. When it is always CFL, you can answer always context sensitive, always recursively enumerable. That's obviously true, okay, using implication concept. Now regular, no. DCFL, no. But CFL, okay, this is the right statement. If you wanted to take an examples, you can take lot, but I don't want any example here. As you know, it is always CFL. You can prove it with the help of context free grammars. Next. Okay, let me change the question. As you know, both are same questions. If L1 is DCFL and L2 is CFL, now here let me change the question by looking at the question 5. Okay. I'm just taking a very simple one. L1 is DCFL and L2 is not DCFL. Okay, very simple. Try to understand the statement. One is DCFL union, another one is not DCFL. In the exam anything could be possible, right? So I'm just framing it. Then what happens to this answer? L1 is DCFL and L2 is not DCFL. So what can you answer it? Is it always DCFL? Is it always not DCFL? So here very simple question. Well, I have a lot of answers for this. Let's try. The first one, is there any example which gives DCFL? Okay, I'm trying that. DCFL I may take, let's say, sigma star. Union I will take some non-DCFL, right? Which could be WW power R. So the answer will be definitely sigma star if you are taking over sigma, right? So you got even regular answer. See that? This is a DCFL and regular, you can say that. Many answers for this. That means sometimes DCFL, sometimes what? DCFL. Is there any possibility of non-DCF that's not DCFL? If I take empty, one of the DCFL is empty language, union, not DCFL. Whatever the not DCFL you take, the same not DCFL comes here. It means the answer may be DCFL or maybe not DCFL. So this question is not having unique answer at all. Not having unique answer. You can't answer any of this, will go to none of this directly, because the answer could be either DCFL or not DCFL. So result will depend on something like need not be DCFL or maybe DCFL, something like that. Okay. Fifth one, if L1 is DCFL and L2 is regular, then what is this union? Very interesting question. And remember this concept, DCFL union regular is, can you think about this? See, DCFL has deterministic pushdown automata. This regular has a finite automata. So there is an algorithm, composition algorithm for DPDA and finite automata. We will get back to DPDA again. Anyhow, when you combine DCFL with regular, you always get DCFL. There are algorithms for this, but if you want to know examples, is there any example that DCFL union regular you will not get a DCFL? There is no such. Okay, DCFL union regular you always get DCFL. Only the problem might happen, DCFL union DCFL you may not get a DCFL. Okay, so I'm just writing the statements. If you perform this is right, first always DCFL, it's because of always DCFL, always CFL comes, so regular not guaranteed, regular not guaranteed. So remember that because of always DCFL you can always choose CFL too. I hope it's done, but I'm just saying that DCFL union DCFL, what did you get? Always CFL you got, because answer here need not be DCFL. We don't believe on DCFL result. It could be different from DCFL. And you have seen one language is DCFL, other is CFL. Answer is still same, that is always CFL. No guarantee of DCFL. So, and also we have other cases, but try to think about these combinations, how do you get. But here when I take one input is DCFL, other is regular, do not assume your domain is only DCFL, that's wrong, right? So here one operand is DCFL, other operand is regular. This kind of there is a special operation called as the regular closures. That means your domain is DCFLs, but operation is regular closure, means one operand is fixed as regular, then other operand will be taken from the domain. So that is called as regular closure. Regular closure. Is it closed here? Yes, it is closed because you got always DCFL. Now you are talking about CFL and regular. This time CFL union regular. What is the result? Similarly, PDA and finite product can be composed, or you can compound both the machines to get back to PDA. Anyhow, it's very clear CFL union regular is the CFL, CFL union DCFL is the CFL, and CFL union CFL is the CFL. Without any confusion, it is always CFL. But answer may not be regular or may be regular, depends on what two languages you have taken. If this CFL is already regular, regular union regular, you may get a regular, but that regular is also CFL. So in theoretically you can always answer CFL, but when the example is given, you should know within the CFL where it stands, within the CFL class where it stands. By looking at this, you can't answer regular DCFL, but you go to CFL. But also look at other statements that you have already done. CFL union DCFL. What is it? Just now we have seen it's a CFL. CFL union CFL. Okay. It's again CFL. Fine. As you know, there are proofs for this. You can write a context free grammar for this. You can write a context free grammar for this second operand, and you can get the result by using the grammar with the help of bar, S1 bar or S2. Next, before going for intersection, let me ask some questions for you. You are doing the union, right? You are doing the union, right? So I'm just going to ask some questions, answer it. First question is, DCFL union if you want to make very interesting table, you can make it. That's also very interesting. I'll make a table for you. Okay. This is union table. Assume you are applying union table. Okay. Fill that table on your own. But I'm just giving a hint. This is the finite language or finite set. And this is the infinite set. As you know, for the exam point of view, union intersection are very, very important, like including complement. Union, intersection, complement, these three operations are really going to help you. Okay. You already have a regular set, you have done them, right? But I'm just giving the hint, deterministic context free language and context free language. Okay. You have here a finite set. You have infinite set, regular set, DCFL as well as CFL. Okay, you have a table, and what you have to answer? You have to answer the union of the row and column. Can you do it on your own? And I want you to fill this table so that, but do not try to remember this table, which may or may not help. As you know, TOC, you have a lot of tables. If you're trying to remember all the tables without any shortcut, you may go to the wrong answer sometimes. So here, let's say closed, that union is, what is the result? What is the result after doing the union? Finite union finite. What is that? I'm just writing equal to, because this is going to perform union, right? It is equal to finite. Finite union infinite, it's equal to infinite. Finite union regular, it is always regular, but may or may not be finite. Finite union DCFL, it's going to be always DCFL. So equal to, you may delete it, but you understand, finite union finite, you got finite. So that equal to I am deleting here, but assume that it's the result of the row and column. Now infinite union finite, it's definitely infinite. As one of the operand is infinite in the union, the whole result is infinite. Infinite union infinite, definitely infinite. Infinite union regular, we don't know whether it is regular or not, but it comes as infinite. So this is a very interesting row. Everything you see infinite because one of the operand is infinite. Here the result always infinite in this row because one of the operand is infinite. Even this column, because the other operand is infinite, so you may answer it is infinite without any doubt. Okay, this is a very simple column and row. As one of the operand is infinite, so infinite union any language is definitely infinite. Now come to the regular set row. Regular union finite is always regular. You may ask, sir, how do you say that? Because regular and finite both will have the finite automata. So you can do the union algorithm, you can approach the union algorithm, how to do the union of two regulars. The same algorithm you can use, you will get regular back. REG means assume regular language. Regular union infinite already done. Regular union regular, no doubt it's a closed, so definitely regular. REG. Regular union DCFL, so it is DCFL. And regular union CFL, it is CFL. Okay. Now DCFL union finite, what is it? Okay, some things union is commutative, so you can fill, either upper triangle or lower triangle. As you know, this union is commutative. Union is commutative. DCFL union finite, it's a DCFL. DCFL union regular, it's a DCFL. DCFL union DCFL, it is the CFL. Oh, it's a very important point. DCFL union DCFL, we know it need not be DCFL, but always CFL. DCFL union CFL is a CFL. And for the CFL union finite, CFL. CFL union infinite is always infinite. CFL union regular is always CFL. CFL union DCFL, always CFL. CFL union CFL is always CFL. Okay. So very interesting table for the union operation. Similarly, you can apply intersection and complement, reversal, concatenation, set difference. But we are going to see some of the examples, and really this table helps you a lot. If you see the previous year gate questions, among them union is one of the important closure property for different domains that you have. Okay. Now we'll go for another operation or another closure property, which is intersection. What is DCFL intersection DCFL? DCFL1 intersection DCFL2. What happens? Really, if you do not have a lot of examples in front of you, maybe you cannot come up with the right answer. So you should have a lot of you should know a lot of DCFLs and CFLs and not CFLs, so that you will get to know what example can help you to conclude it if you don't have an algorithm. Definitely, if you don't have an algorithm, you can't prove always DCFL, right? So now I'm going to take an example here. You already know something like a power n, b power n, c star. This is one language, let's say, where n is anything. Intersection, if I take a star, b power k, c power k. What's happening here? Here a's and b's are equal. Here b's and c's equal. So that if you do the intersection, Here A's B's should be equal. To satisfy this B, C should be equal. You will get one example, A power, B power, C power should be same. Then only it can satisfy both these strings or both these languages. Okay. Now what did you conclude? This is DCFL1. This is also DCFL. But intersection, you did not get a DCFL. This is not a DCFL. Not only it's not DCFL, it is also not a context-free language. What is this language? It is a context-sensitive language, which is outside the context-free language class. So this is very interesting language. With this, you can conclude the intersection is not closed for DCFLs, because you see the example, the result goes outside the domain of DCFLs. Fine. If you ask me, sir, intersection of two DCFLs, can you give an example of DCFL? That's very easy. You take the same language again here, you will get the same, right? Proving the same is not difficult. Problem is there any example which goes outside the domain? Yes, there is an example. So now I can conclude it's need not be DCFL. Need not be DCFL. Now you may ask the question, sir, DCFL union DCFL, we got always CFL. Can we get the same thing here, always CFL? No. See here, this example already proving not a CFL. Means when you take two DCFLs, perform the intersection, you did not get a CFL. It means the intersection of DCFLs, you can't prove always CFL. It is also going to be need not be CFL. Why you don't have an algorithm? Because you can't prove always CFL. This is the best example where it is going to answer need not be DCFL, also need not be CFL. Whereas the union, it was always CFL, so we had an algorithm to write a grammar. You can write the grammar for the two languages, but you can do the union. But for the intersection, you don't have a proof. As you see, you don't get any conclusion directly within the domain. Okay. Now this example is a very good example to give the counter proof, or you can say to get the outside the domain language. This example would be sufficient. You took two languages from the same domain of DCFLs, but the result goes outside the domain of DCFLs. That's why we say intersection is not closed. Now what do you conclude? Is that intersection of two DCFLs is a regular? Wrong. Intersection of two DCFLs is a DCFL? Wrong. Intersection of two DCFL is it a CFL? Wrong. So remember this point, DCFL intersection DCFL, you may not get a DCFL too. Very, very important point. When you look these theoretical lines, DCFL, DCFL, intersection, oh, it be DCFL, that's wrong. Right? You can't say always DCFL. Sometimes DCFL, sometimes not DCFL. So for that, I have just given an example here. Okay. So it depends on what languages you take. If these two languages are DCFL, you may not get DCFL sometimes, but sometimes you will get DCFLs, sometimes not. Next, CFL. Okay, will the same example work here? CFL 1 intersection CFL 2. You already taken an example, right? The same example you can take here. Same example, A power n, B power n, C star, and here A star, B power n, C power n. So when you take that, you get here need not be CFL. But what do you get always? Context sensitive language, as you may aware or not. If you are aware, CSL intersection CSL is always CSL. So you can assume these two are CSLs and you can prove using context sensitive language algorithm. But you have to remember this point, it's going to be always context sensitive language, even for the DCFLs too. Okay. Same example you take like A power n, B power n, C star intersection. It's a one set. Another set is A star, B power n, C power n. So you will get A power n, B power n, C power n. And this is called as context sensitive language, which is not a DCFL, not a CFL, but it is a context sensitive language. Okay, both are, you can assume CFL. Previously I was assuming they are DCFL. Now you can assume even CFL. So this three cannot be answered right now. So none of this is the right answer. Okay. Next. Now very interesting. DCFL intersection context-free language. What is it? I'm trying to say something which I did something wrong during my BTech. What was that my mistake is? I used to assume this box is a DCFL and this box is a CFL. Wrong. This box is not a DCFL. This box is what? All DCFLs. It means set of all DCFLs. It is not one DCFL. It's combination, all DCFLs. Where is the DCFL? Here somewhere the DCFL exists. Somewhere DCFL exists. Okay. I used to assume that way. This is a DCFL intersection CFL. So CFL is answer. That's wrong. What is the right answer? This box is not a CFL. It is a set of all CFLs. Here, what is that? Set of all DCFLs intersection set of all CFLs. This you get set of all DCFLs. That's true. But using this logic, don't conclude here. You may not have a relation with this DCFL only. Then how can you assume this DCFL with some CFL? CFL might be here anywhere. Understand, these two DCFLs only, you don't have the relation sometimes. Then how can you conclude the DCFL intersection CFL is the DCFL? Completely wrong. Here, do not assume such things. We are not doing this box intersection, this box. This box is already having infinite DCFLs inside. An intersection with all CFLs. The result is again all DCFL but not one DCFL. Remember, this is about one language. I might be asking this language intersection this language. You don't know. The result need not be DCFL. Already we have seen when you do two DCFLs intersection only, the result is need not be DCFL. Even that was need not be CFL. Then how this can be DCFL? Wrong. Okay. So this comes under same need not be DCFL. Not only this, need not be CFL. The same example that you have taken in the previous two questions, same examples are applicable here also. So what is the right answer? Regular wrong, DCFL wrong, CFL wrong. So we go to none of this. Okay, very interesting question which was asked many times in the exam too. Okay, this is a regular property called as DCFL intersection regular. One of the operand is regular. Then what is the result when you apply for the DCFLs? DCFL intersection regular. So you can say simply the name is called as intersection with regular languages. Because your domain is DCFLs now, I want to perform intersection with regular. Then what is the result? Is always DCFL like union. Okay, it's always DCFL. It's always DCFL. And here also you have the algorithm to prove it, but right now we are not going into that details. But if you want to take any number of examples, you may try. Okay, I'll just try the pi intersection anybody. Okay, any regular. Pi intersection regular is definitely pi. And take a power n, b power n intersection, something like a plus b whole star. It's a power n, b power n. Likewise, you take any number, but this is always DCFL. Whether it is regular or not, this is regular, but this is not regular. So result is regular or not regular, but always DCFL. So that's what we are talking about. So what is your conclusion? Regular, no guarantee. So do not assume again, this regular is inside the DCFL, sir. So regular intersection DCFL, why not regular? So don't ask such very, wrong questions. That's completely wrong question, right? I just told you this regular is not the box. It is, it's not that class. The class of regulars is different from one regular. Okay. So I've just given example here. You take this example, it's regular and DCFL. Why are you not getting regular? So don't think that way. That's not just one word. It's the meaning of the language. Okay. It's always DCFL. So can I say always CFL? Yes. So it's, if it is MSQ type, then choose this two. Okay. here DCFL, so you can say always CFL. Next, what about CFL intersection regular? L1 is CFL, L2 is a regular. If L1 is CFL and L2 is regular, what is the intersection of CFL and regular? CFL and regular intersection. What is it? It's again always CFL, but may or may not be regular, may or may not be DCFL, but always CFL, always CFL. It's not only this, even DCFL intersection regular is also always DCFL. So always this operand other than the regular, you see somebody else, right? The same one will be the answer. Okay, remember, even for the union, when you do DCFL union regular, what did you get? You got a DCFL. When you are doing with the regular, the result depends on the other operand only. Even CFL union regular, it's CFL. Okay, do not include finite and infinite languages here. They are completely different from these domains. Okay, so when you are doing union or intersection with regular, the result will depend on other operand only. Okay, so now you can answer CFL intersection regular is CFL. This is your answer. So you don't choose regular and DCFL, you will go for CFL. You will go for CFL. Now, if L1 is CFL and L2 is finite, it's a very interesting question. Then L1 intersection L2. So CFL intersection finite language. What happens? You know, in the intersection, if one of the language is finite, the whole result is finite. All result is finite without any doubt. Because this is the maximum that can be common with the CFL that will happen in the result. When it is finite, can I say it is always regular? When it is regular, it is always DCFL. When it is DCFL, it is always CFL. So that means it is concluded as all these answers are correct. As it is a finite language, every finite is regular, DCFL, CFL. Okay. So you are talking about one direction only, so definitely correct. Definitely correct. So CFL intersection finite, not only CFL intersection finite. In future, if I ask DCFL intersection finite, what is your answer? Finite only. Even regular intersection finite. This finite language has a very interesting property. You do not require any machine to prove it. Even infinite language, you take intersection finite. It's definitely finite. Okay. Now, complement operation. This is really important for you. Complement of DCFL. There is a DCFL. If you do the complement, what do you get? You know, there is an algorithm in DFA. The same algorithm will be applicable here. Like for every DCFL, let's say I am taking a DCFL. Let's say this is L. And you construct a DPDA for this. But use the deterministic transitions. Don't ignore the transitions. From every state, you try to take the combination for input as well as top of the stack. We ignored some of the combination when you don't want as a valid configuration. But this time, you take all the configurations from every state, design a DPDA without missing any combination. So this DPDA, when you interchange finals and non-finals, you get another DPDA, and this is going to accept DCFL, which is exactly L complement. So if L has the DPDA, L complement will also have a DPDA which is having an algorithm to prove it, similar to DFA, deterministic finite automata. So now complement of DCFL is a DCFL. Sir, can you give some examples which I did not see in regular? Yes, you can take some of the examples. You try A power n, B power n, do the complement, and this is already DCFL, right? Do the complement, you get it's a DCFL only. This is the DCFL. A power n, B power n is a DCFL, its complement also DCFL. You take any DCFL, not only this one. You can take regular, you can take finite language, all are DCFLs only, right? You can take any DCFL, do its complement, you get a DCFL. But for that you need to follow an algorithm, right? It's not just saying, it's not that easy to do that. I'm not showing how it is DCFL, but I'm proving it with the algorithm. Okay, if anybody want to learn that, you just try to prove it. To consider the DPDA and interchange final non-final, then you get another DPDA. It will definitely accept the complement. But how do you consider the DPDA? This DPDA is very important. You need to design DPDA such a way that the interchanging final non-final should get the right answer. Okay, so now the DCFL complement is DCFL, but every DCFL is what? CFL. Can I say DCFL complement is a CFL? Yes, every DCFL is what? CFL. You can say that. Okay, next. CFL complement. CFL complement. DCFL complement is DCFL because you have a proof, but complement of CFL complement, actually you may or may not get a CFL. So may or may not be CFL. For that, you should have the proper examples to learn. Let me take the first one, CFL example. Okay, I'm just taking L1, which is CFL. That you can take DCFL or anybody, right? So you can take any example. Let's take A power n, B power n. When you do its complement, this is, I'm assuming CFL. Okay, we know it's a DCFL, but I'm assuming CFL. So what is this? L1 complement is CFL only. It's already DCFL, so definitely saying CFL is okay. Now I'm just saying something different. L2 WW such that W belongs to A comma B whole star, and this one already taken the complement. Remember that this L2 is complement of this. This is what? Context-free language. You have a PDF for this, you have a context-free gamma for this, but when you do its complement, that is L2 complement, it's WW. What is right here? L1 complement is what? L1 complement, you got A power n, B power n. A power n, B power n bar. We know this is also CFL. But what is L2 complement comes? WW. That's WW is, of course, such that W belongs to A comma B whole star. You say that is not CFL. Okay, assume W belongs to A comma B whole star. And these are very two important examples. This both are CFLs, but when you do the complement, you may get a CFL, you may not get a CFL. That's why CFL complement may or may not be CFL. Definitely you will have a question, sir, why this is CFL? Obviously, the whole video, how much time it took, the one problem will take the same time. That's why I'm not touching why it is CFL. In case if you are so interested, definitely you can come for the practice classes, then you can ask this doubt. Fine. Now, CFL complement need not be CFL, so don't choose any of these three options, go to the none of this. Okay. If L is DCFL, then what is reversal of DCFL? Very interesting question. You have a DCFL, some DCFL, you are performing its reversal. You are performing its reversal. What happens? Will you get a DCFL? Do you have any algorithm to do the reversal concept on the DPDA? But you have an algorithm in DFA. Here you will not have an algorithm. The reason is the result may not be back to DCFL, but it is guaranteed always CFL, because in a context-free grammar you can do the reversal of every production in the grammar, you get a reversal of a language. Very interesting concept. Like union, Union of two DCFLs, you got a CFL. Here also reversal of DCFL, you get always CFL. Sometimes maybe, sometimes DCFL, sometimes not. Do you have any such example? Reversal of a DCFL, you don't get a DCFL. Do you have any such example? I'm just giving an example. Reversal of DCFL is not a DCFL. Okay. Is there any example? Reversal of a DCFL is not DCFL. Now you are going to perform reversal of a DCFL, you should prove that it is not a DCFL. Think about it. When I am reading from left to right, I have a deterministic stack. But when I am doing from reversal, you don't get sometimes deterministic stack operations. Look at, I am keeping C in the beginning. This is very simple, A power n, B power n. This is one type of the strings in the language, same language, and other type of the strings in the same, it is a one L only. Okay, don't assume two languages. There are two types of the strings in the same language. Other one, you have a D, let us say A power n, B power 2n. So now I am very clear, if my string starts with C, I will go to this side, I will do equal number of A's and B's. If my string starts with D, I will go to this side, I will just ensure that B's are twice to the A's. So that can be guaranteed, because the first symbol C and D are clearly giving a hint how to perform the comparison between A's and B's. But when you do the reversal, what happens? This is the DCFL, everybody should agree. This is old language I am talking about, this complete language. It is the one language, right? Do not assume two languages. Now I am doing the reversal. Perform the reversal on this language. What happens? These strings will do the reverse, like B power n, A power n, C union. These strings also will go in reverse, A power n, D. Now will it be DCFL? See, B's are coming in the beginning. B's you may push, but A's how you compare with the B's, because the C and D is there at the end. So you can't go to C and D, you can't come back, right? So you are moving from left to right, but you will do a single scan. You don't do multiple scans because your head moves only one direction. Now this here, B power n, A power n and B power 2 and A power n, two types of the strings you need to judge without looking at C and D. That's really difficult, because B's I may push, but A's what to do? Here 1A, 1B I have to pop, if that is a string. If the string is here, the 1A I need to pop the 2B's are really challenging for us now. So this is not a DCFL. What is it? It is not a DCFL. Okay, that's what I have given. I have taken DCFL, its reversal I have shown not DCFL, but in general that need not be DCFL is right, because sometimes if I take simply the language is L is equal to A power n, B power n, what is its reversal? B power n, A power n, but both are DCFL. That doesn't mean that every time you get a DCFL, right? Some DCFLs, their reversal definitely you may have the DCFL sometimes, and some DCFLs their reversal is not DCFL sometimes. Okay, this by considering these two, we have answered the result may either DCFL or not DCFL, but it's always CFL. The reason is, once you have the context free grammar for this, by doing the production reversal RHS side, every production do the reverse, you will generate this. So it's very easy to say CFL reversal rather than DCFL reversal. Anyhow, the DCFL reversal is need not be regular, need not be DCFL, but always CFL. Okay, always CFL. So using this concept, now you can answer very easily. CFL reversal is definitely CFL. Okay. The proof is here, very simple proof, that is, if I give you CFL, let us say L, what you write? Write a context free grammar. Write a context free grammar. Let us say this is a G. What do? you are going to perform the reversal. Perform the reverse every production. Reverse every production, then you will get another CFG. So this is, let's say, G dash. Then this CFG will definitely accept the L power reverse. That's a CFL reversal. Definitely this is CFL. So CFL reversal is CFL. Proving is so easy. And in case if you want an example, you have, let's say, A power n, B power n language. For this you can write a grammar. S derives AS, B or epsilon, and do the reversal. So ASB become BSA, epsilon become epsilon. So here you get something like S derives BSA or epsilon. So it's reversal, and this one is going to generate B power n, A power n. So this is how you can prove why every CFL reversal, again you get a CFL, because CFG exists for CFL, it implies CFG exists for its reversal. Okay, it's definitely CFL, but DCFL regular we cannot guarantee. Fine. DCFL reversal also CFL, CFL reversal also CFL. Okay. Before going to the concatenation, let me give you some interesting table for you. In your intersection you make a table like union. So I am giving for the reversal, also you may do for the complement in case you are interested. Okay. What do? It's just unary operator, right? So it's just do simply. Okay, let me think about a different way. Reversal, it's unary, right? And then complement, this is also unary. So I'll make two rows separately. One for finite, infinite, regular. Only one input required, right? That's why you don't need a row and column the same language. DCFL and CFL. Okay, others we are not worried right now. You can ignore anything else you want later. So I am going to make table here. This is a table. Now what is the result you see? Reversal of a finite. You know it's the same, right? Same finite language. Infinite reversal is also infinite. Regular reversal is a regular. DCFL reversal is DCFL. Is that? No, right? So that's what. So you cannot simply go and answer everything. What is a DCFL reversal? I have just given an example. When you are reading a language from left to right, you will have the deterministic stack operations, but when you do the reversal, you can't do deterministically, but you can do non-deterministically. So you get a CFL, and CFL reversal is CFL. So what is important here? This is very important. Okay, this entry is important. We may do the mistake, and reversal of a DCFL, do not say just DCFL. Sometimes DCFL, some examples you see DCFL, but are not all the times, but always the CFL. Complement of a finite language, you have seen that it's going to be infinite. Over the sigma, the complement of finite is always infinite, because from the sigma star, when you delete the finite language, you will left with infinite always. Infinite complement we don't know, that's guaranteed. So I'll just say may or may not. May or may not, infinite. Okay, it depends on the language. If you take the sigma star, do the complement, you will get a finite language. Regular complement is regular, we have algorithm. DCFL complement, very interesting. DCFL, see that this is also very interesting. CFL complement, it's you get a context sensitive language, but you don't get or you don't say don't get, you may or may not get CFL. Okay, context sensitive language you get. Okay, here answer you may say may or may not be CFL, but always context sensitive language. As we don't know about context sensitive, you can ignore it. So very interesting table for you, complement as well as reversal. In case you see something which is explained that you don't know, you can discuss in the comments. Next one. Now we are going for concatenation. Obviously, the concatenation somewhat different than the union intersection. Okay. Two DCFLs concatenation, DCFL1 dot DCFL2. What happens? We know finite dot finite is finite, infinite concatenation with infinite is infinite, regular concatenation with regular is regular, but DCFL concatenation with a DCFL, what happens? Will you get a DCFL? DCFL concatenation with DCFL, will you get a DCFL? So think about these cases. DCFL concatenation with DCFL, do you get always DCFL? What happens? Do you have examples for this? So I am just giving a homework, as I have shown you in union intersection. I am just giving homework. Definitely you will find a reason. Concatenation is not closed. The result you should get need not be DCFL. It means there is example. You take a DCFL and you take a DCFL, its concatenation, you will not get a DCFL. You will not get a DCFL. So I want you to think about it. Obviously, you have answers already, right? I will just show you. I am giving answer. L1 a power n b power n such that n greater than or equal to 0. L2 a power n b power 2n such that n greater than or equal to 0. You know, when you concatenate, don't use all of them same power. Okay, remember that when you concatenate, the result is something which is, you know, L1 and L2 very easy. L1, L2, right? When you do this, what happens? A power n1 b power n1 dot a power n2 b power n2. Sorry, what is that? 2n2. n2 b power 2n2. This is how you should write concatenation, because when you are putting in the same string form, then you can't have all or n. If you are writing all or n, that means you are saying that all the 4 have a dependency. But in fact, here these 2 are having dependency, these 2 are having dependency, but not all 4 together. And now what happens? When I start with A, now B. This B belongs to which one? Is this B belongs to this one or this one? That you don't have a guarantee. I have given homework, I am giving examples, just you need to understand what is happening. This B, is it belongs to this one or this one? Really you don't know. Why? This might be epsilon. If this is epsilon, you might be assuming this B should pop 1A. That's wrong, because here you need to, every 2 B's you need to pop 1A. This B might be here or might be here, depends on the value of n1. If value of n1 is 0, then this B belongs to here. But you don't know, right? The string always comes like this. Then this B, you have to take non-deterministic choices. If this B is here, then for every 2 B's you pop 1A and you will stop at the end. If this B is here, after popping A's for every B, then this A's might begin later. So what comes in the future is you do not know, but this B you have to take the decision deterministically, but deterministically impossible. As you know, this B might be belongs to this one or belongs to this one, and this A's you may take a decision, push all the A's, but this B you can't take unique decision. That's why the result of this one is going to be not DCFL. This is not DCFL. Even though individually both are DCFL, when you concatenate, you don't get a DCFL for this example. Anyhow, you have lot such examples. Okay, you have examples, but think in a possible way where you can conclude the correct answer. So now, is it always CFL? Oh, that's very important, right? It is going to be CFL, because non-deterministically you can do. Like you can write a context free grammar, like for this S1 is a start symbol, for this S2 is a start symbol, you can write S1 dot S2. And what S1? The one grammar you already have. What S2? Other grammar you already have. Just put all of them into single grammar. The whole grammar will become the new grammar for the concatenation. Okay, very simple algorithm you have. So it is always CFL. So you can go for this, but don't choose this too. Okay, saying DCFL definitely wrong. So you have to, you should know why we say need not be DCFL. It could be possible sometimes 2 DCFL concatenation is DCFL, but you need to learn with the example. For the same question, if a small change I do it for the same one, this 0 I make it 1, then definitely this AB always happens. So this B you can say it is always here because you said at least one B is there. Then this N1 is at least one value. So 1A 1B definitely guaranteed. So this B you can guarantee. So if I put this N1 condition is greater than or equal to 1, then this concatenation will become DCFL. A very small change can make the language. Okay, so keep that point with you and put here, if you put instead of 0 1, this concatenation will become DCFL. But you should think right way which concatenation is DCFL, which concatenation is not DCFL. Okay. Next, obviously, right, just now I told CFL1 dot CFL2 is going to be always CFL. How do you prove it? You just write a grammar for this, right? One grammar with G1, G1 as a context free grammar, S1 as a start symbol, here G2 as a context free grammar, S2 is a start symbol. Here you can write a new grammar combining CFG1, CFG2 along with a new start symbol S1 followed by S2. Okay, so very simple. You can prove it always CFL. So you don't choose regular DCFL, but always you choose CFL. Now you got to know the many things that are going to come into picture. You think about a lot of homework questions like CFL dot DCFL what happens and CFL dot regular what happens. So think about all such questions. I am giving you homework for that. Now concatenation, that is what I am saying. DCFL dot CFL, what happens? Already we know DCFL dot DCFL, no guarantee of DCFL, but DCFL dot CFL, can I guarantee always CFL? Yes, because for this I can write a context free grammar, I know what is the algorithm to do the concatenation of these two languages. So it is always CFL, always CFL, but these two no. Okay, I said homework, but I am trying to explain DCFL dot CFL and CFL dot DCFL. It's going to be always CFL. Maybe regular, may not be regular, maybe DCFL, may not be DCFL, but always CFL. Okay, some homework questions should be there, but we'll see at the end. L1 and L2 are DCFLs, then what is the set difference? Can you take this as homework questions for the set difference? I have explained for union, I have explained for intersection, I have explained for the complement, I have explained for the reversal, I have also explained for concatenation. Now the set difference. Can you think about it? DCFL 1 minus DCFL 2. What happens? If you want to think about L1 minus L2, there is another way to think about L1 intersection L2 complement. We know DCFL complement is DCFL, but DCFL intersection DCFL, no need to be DCFL. With the help of that concept, right, the same one you can also write other way. So when you are saying DCFL 1 minus DCFL 2, you can think this direction, DCFL 1 intersection DCFL 2 complement. You already know DCFL 2 complement is DCFL, right? So DCFL 1 intersection some DCFL, this no need to be DCFL, need not be DCFL, but can I guarantee always CFL? Yes. So here need not be DCFL. Examples you can take from the intersection already. but always, oh, always also it's a I'm very sorry. Why do you say always CFL? So do not, when you don't explain, don't say blindly it's always CFL, okay. Doesn't mean that it need not be DCFL, doesn't mean that it is always CFL, okay, that's wrong. When I do, sometimes when I don't explain properly, I go with the wrong statements. That's why you need to, when I say something, you need to have a reason. So now can I say always CFL? Can I say always CFL? So is there any guarantee DCFL intersection DCFL is always CFL? Intersection of two DCFLs, we already know it need not be CFL too. Okay, we already seen that. The same concept comes here. That's why immediately I stopped what I am speaking. Okay, we already know this point. Go back and look at intersection of two DCFLs. We say need not be DCFL, we say need not be CFL, because we are getting context sensitive language always. Okay, that's why the not only DCFL minus DCFL, CFL minus CFL also same answers comes out. So regular, DCFL, CFL we fail, so none of this. Answer is same, the CFL 1 minus CFL 2. What happens? Two CFLs, set difference. It's going to be need not be. Already we got for DCFLs. Inside, when we take DCFL, already we got need not be CFL. Same example will work here. Okay, but in both of them, you can prove that always context sensitive language. Even the previous one also, DCFL minus DCFL, you can say always context sensitive language. Fine. Here, if you want to think about examples, you can take the intersection example, you can work on it. None of this. What about DCFL minus CFL? You can use the same concept. You can see DCFL minus CFL, it means DCFL intersection CFL complement. This CFL complement already we know it's need not be CFL, but it is a context sensitive language, and this comes as context sensitive language. So here always context sensitive language comes, but need not be CFL, okay, need not be CFL. So we don't choose any of these three options, okay. Even CFL minus DCFL, what about CFL minus DCFL? CFL minus DCFL, CFL minus DCFL, what do you get? CFL intersection L1 minus L2 means L1 intersection L2 complement. DCFL complement is what? Sorry, this is CFL, right? CFL, okay, just copy paste. CFL intersection DCFL complement is what? DCFL. But CFL intersection DCFL, CFL intersection CFL, DCFL intersection DCFL, this is always CSL, context sensitive language. So it is also going to be the same answer. Always CSL, but need not be CFL, need not be DCFL. Okay. What about the CFL minus DCFL? Just now we answered, right? DCFL minus CFL, CFL minus DCFL, both are going to be CSL, context sensitive language. Okay, I am just deleting it. Now this is a different one. DCFL minus regular. Here you are doing subtraction with regular, so you should be very careful. DCFL minus regular. What happens? The same L1 minus L2. Remember this point? L1 minus L2 means it's only L1 which is not in L2, which is same as L1 intersection L2 complement. So outside the L2, what is common with L1? That's only L1 portion. Okay, and remember this point. Now I am writing DCFL minus regular means DCFL intersection regular complement. What is regular complement? It is regular. What is DCFL intersection regular? We already know it is DCFL. So this is always DCFL. So clearly understand, intersection with regular, DCFL intersection with regular is always DCFL. Okay, we know this point. When it is always DCFL, so always CFL. So remember this point. When you choose DCFL, if it is MSQ type, look at, there is another option which is there, CFL. So CFL. No need to write that. So CFL. Next, DCFL minus regular. Did I do the same? DCFL minus regular, but this time L2 minus L1. So look at this. You need to read carefully. Previous one was L1 minus L2. See here, regular minus DCFL. What is the difference? Yes, there is a difference. Previously regular you did the complement, but here you are going to do the DCFL complement. To answer this, what do? Regular intersection DCFL complement. But luckily we know DCFL complement or complement of DCFL is always DCFL. So we get the same back. Regular intersection, same type of language you get. Then this is, we just saw DCFL intersection with regular is always DCFL. So we can conclude it is always DCFL. So CFL2. Every DCFL is what? CFL. Fine. So regular minus DCFL, DCFL minus regular, both will be concluded as DCFL. Maybe the languages are different. Okay, maybe languages are different, but the result always stays as a DCFL. Now, very interesting. This time, context free language minus regular. L1 minus L2, CFL minus regular. L1 is a CFL, L2 is regular. What happens when you do the subtraction between these two languages in a particular order? It may be regular minus CFL could be different answer here. That is why we are coming to this kind of examples. CFL minus regular, what comes as CFL intersection regular complement. What is regular complement? Is regular. So we already know CFL intersection with regular is always context free language. So you can answer it as context free language. So you can pick this. Okay, these two are absolutely, they are not always. Now, interesting point is L2, that is a regular. Regular minus context free language, which is going to concluding as a different answer now. So what is that different answer? Can you think about now? This regular L1 minus L2, I am writing L1 intersection L2 complement. What could happen to the CFL complement? CFL complement need not be CFL, but we know it is going to be always CSL, context sensitive language. So this concluded as context sensitive language. So very interesting, this CFL minus regular is always CFL, but regular minus CFL is not, need not be CFL, need not be CFL. So keep this point in mind. Remaining are coming to known answers, but this one goes outside the CFL, don't say outside the CFL, but the always CSL. It may be inside the CFL or outside the CFL. So you don't choose any of this, go to none of this. Next, now we are going for again reversal of DCFL. I didn't ask, read the question carefully. We know reversal of a DCFL need not be DCFL, we know that, right? If anybody takes DCFL, do the reversal, what happens? You said already need not be DCFL. I didn't ask this. This is a different question. We know it is always CFL. So always we should know what question is given here. It's not asked reversal of a DCFL. What did it say? L power reverse is equal to DCFL. If this is given to you, then what is L? Is it regular? Is it DCFL? Is it CFL? So this is what you need to think. Can you guarantee always DCFL? That's what I am asking. Is there any example? Not a DCFL reversal, you may get a DCFL. There only answer is there. Sometimes DCFL reversal, when you do it, you may get not DCFL, right? Take that not DCFL, do the reversal, you will go back to DCFL. Here L may be DCFL or not DCFL. Giving DCFL, you have lot of examples. You can take a regular language also, right? Its reversal is regular, so both are DCFLs, but not DCFL. You can take when you do the reversal, you got a not DCFL. You remember that example, like C and D you kept in the beginning, right? So take not DCFL example like this, A, okay, if you remember that, B power n, A power n, C union B power 2n, A power n, D. This is not a DCFL. And do its reversal, you will get a DCFL, because C and D comes in the beginning. So that's what I am trying to say. Even though it is not DCFL, but do its reversal, you will get a DCFL. That is, L power reversal is DCFL doesn't mean that L is DCFL. It may be DCFL, it may be not DCFL. So what can you conclude? But it's always going to be, but L is always CFL. As you know, the reversal, when you get a result is DCFL, it's always going to be CFL. Okay, you can conclude CFL but not DCFL regular always. Sometimes okay, sometimes okay. What about this same? Oh, this is very interesting. In this you can write two directions. Why? Because L is a CFL, L power reversal is CFL. We already know this direction is true and now this direction is also true. Whenever L power reversal is CFL, L is also CFL because its reversal is the same concept. For this you write grammar, context free grammar, reverse every production, you will get back to L. So this reversal of L is CFL, that L is also you can conclude as a CFL, no doubt. Okay, use this concept only for the DCFL proof. When a reversal of L is DCFL, that means for that you have a context free grammar. Definitely L is what? Do the reverse, you will get a another context free grammar. So I can assume that always CFL in the previous example too. So I hope you have no confusion here, because same algorithm approach in reverse direction. For this you write a context free grammar, do the reverse of every production, you will get back to the context free grammar for L. Okay. Next, complement of L is DCFL. It's again I am saying I did not ask complement of DCFL. That's different. We already know DCFL, when you do the complement, what happens? It happens as DCFL. But I didn't ask that way. Now this question is different. If complement, if L complement is DCFL, then what is L? Right. So understand, these two questions are different. Here DCFL complement is what? Here L complement is DCFL, what is L? Okay. Anyhow, same algorithm, right? L complement is DCFL means for L complement you can design a DPDA. When L complement has a DPDA, by interchanging final non-final, L will also have a DPDA. So L is definitely here DCFL. So if it is DCFL, then definitely it is a CFL. You can choose that point. Here I did not ask if and only if. In case if I ask if and only if, you can't choose this option. Okay, let me write that point. What is that? Complement of L is DCFL if and only if L is dash. Here definitely you should answer only one thing, which is DCFL. You can't answer now CFL. If L is CFL, complement of L, you can't say DCFL, right? So here this has to be DCFL. So in this case, when you have option A regular, B DCFL, C CFL, D none of this, then you have to choose only this one, not any other, because this time you need to hold two directions. Complement of L is DCFL implies L is DCFL. When L is DCFL, complement is also DCFL. So two directions you need to hold. So only this statement is true. Okay. Understand the difference between this statement and another statement. Of course, this statement is also correct, but here only you can choose DCFL, you can't choose a CFL. Now, what about complement of L is CFL? If somebody is saying L complement is a CFL, then what happens to L? What can you say about L? Is regular? Is it regular Only regular complements are CFL? No, right? DCFL complements are only DCFL complements are CFL? No, right? Only CFL complement are CFL? No, right? This L can be even context sensitive language. Some of the context sensitive language, their complement can come inside the CSL anywhere, that is CFL. We already know WW is not a CFL, but its complement is CFL. So when you take that example, here I am just taking L is the WW. This complement is CFL, but WW is not CFL, right? In general, L need not be CFL. So what is the answer here? Need not be CFL. But guaranteed that if complement of L is CFL, L is guaranteed it's going to be context sensitive language at some point of time, but that costs you. But you can't choose any of this. But none of this is right. DCFLs are closed under. Can you conclude now what DCFLs are closed under? In case if you have not studied, just remember for these points, DCFLs are closed. Remember, when they are asking about closed, only few operations are closed for the DCFL. Remember, what are closed for DCFLs? One is the complement, other one is prefix, very important, other one is finite subset, complement, prefix, finite subset, another one is H inverse, homomorphism, inverse homomorphism. So look at now, union not closed, intersection not closed, complement closed. That's all, because most of the that you see in regulars and finite languages, among all of them, like clinic closure, reversal, complement, when you compare all of them, these are the few things, 4 operations which are closed for DCFLs. When you compare the main operations, of course there are many operations are closed, but these are the expected gate questions. CFLs are closed. When you talk about the closed, very big list is there for the CFLs, okay? Remembering would be difficult, but not closed you may remember, okay? Closed means union is closed, intersection is not closed, complement is not closed, so here union is only closed. But when you are talking about the big list for the CFLs, many things are closed. Union closed. What else is closed? Concatenation is closed, dot. Intersection complement is not closed. Set difference is also not closed. What else is closed? Reversal is closed. What else is closed? Substitution. There are many other, right? Substitution is closed. Homomorphism, inverse homomorphism, many are closed, like prefix, suffix, substring, many big list. H inverse closed, prefix closed, suffix. I am talking about context free languages. Substring closed, okay? Very important operations. Union along with these operations, they are all closed, but intersection, complement, and what else is not closed? Set difference is not closed for context free languages. I am talking about context free. Now I am talking about not closed. Not closed is very big list, except that for everything else, right? Like, prefix is a closed one. Okay, how do I mention previous one? Did I mention correctly? The CFLs are closed, right? Union is closed. Now DCFLs are not closed. Prefix is a closed, so you can't choose it. Don't assume cross mark is not closed. No, I am choosing the right statement for this. This is closed, that's why I am not choosing it. Okay. Better when you confuse with the cross mark, tick mark. So remember it. This is the closed. Suffix and substring, they are not closed, that's why I am choosing it. Okay. B and C are not closed. Okay. Suffix and substring operations are not closed for DCFLs. Prefix is closed. We have an algorithm similar to a DFA algorithm. Similar algorithm you can apply to DPDA too. Context free languages are not closed. Again, not closed is very small list, like you have intersection and complement, likewise subset, very small list we have. So you can remember for the context free languages. Okay. prefix is closed, suffix is closed, substring operation, all are closed. So you can't choose anybody because these three are closed. So we'll go for the option D instead of choosing ABC. But you have a very big list. They are not closed. Intersection, complement, subset, and there are many other operations like infinite union, infinite intersection, and set difference, L1 minus L2, like finite union, finite intersection. They're all finite union is closed. Infinite I'm talking about, sorry. Infinite union, infinite intersection, infinite concatenation, infinite substitution, infinite subset, they are all not closed. Okay, I just mentioned it, but don't use the finite union. Why finite union? Union is closed, so finite union is also closed for the context free languages. Can you remember some of the important things? For remembering, I have just included these examples. Which of the following? Of course, when you look at this, you will not understand unless you have already proven this, you have already seen examples, then only you can understand these theoretical lines. In the exam, just this theoretical lines only there, but behind you have already done much enough work, that's why you can answer within seconds. Which of the following closed for DCFLs? Already repeated, right? So what are closed? Nothing. Union is not closed, so finite union not closed. Intersection not closed, so finite intersection not closed. Concatenation not closed, so finite concatenation not closed. What is closed then? What is closed for DCFLs? Closed here, complement, prefix. I told the four things, H inverse and then finite subset. Finite subset, that's it. These four operations are closed for DCFLs, very easy to remember. Which of the following closed for context free languages? Context free languages, right? Union was closed, so finite union is also closed. There is a relation between union and finite union. Infinite you can't relate with the union, but union and finite union you can relate. If union is closed, definitely finite union. Intersection, we know it is not closed. How finite intersection is closed? No, right? Very simple. Concatenation was closed. Use the same algorithm finite number of times, you get this finite concatenation. Okay. So here finite union and finite concatenation are closed. Which of the following closed for DCFLs? Subset is not closed for all the domains that we study, like regular, CFLs, DCFLs, CSLs, in future whatever you study, right? It's not closed, but we want for closed, right? Substitution is closed for, sorry, CFL is closed, but it's DCFLs, substitution is not closed. Okay. For CFLs, it is closed. Homomorphism not closed. How do you know that? Just for you remember, right? What is closed? Prefix, complement, finite subset, inverse homomorphism. Anybody did you see here? No. Homomorphism is not closed, but inverse homomorphism is closed. So none of this. These three are not closed for DCFLs. But among these three, the substitution and homomorphism are closed for context free languages. We have proofs for them. Now closed for context free languages at this point of time, substitution anyhow not closed for all regulars and DCFL CFLs, but substitution is closed for regulars as well as closed for context free languages. Homomorphism is also closed for regulars, also closed for context free languages, but not closed for DCFLs. Okay, anyway, we don't go for this option. Okay, which of the following operations are closed for both context free languages and DCFLs? Both are different domains. Individually we should look at, don't combine them. Okay, so that's my individual look. Is finite subset closed for CFLs? Finite subset, actually when you talk about this, I'll make a table here. Regulars, okay, even you can make a big list. DCFLs, even I'm talking about other domains also. CFLs, what about finite languages? Anything. Finite sets, infinite sets, you can make that table if you want it, right? Infinite sets. Think about regular, closed, 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 closed. Oh, sorry, one thing is missing here, this one. Infinite sets, the finite subset of infinite language, you get a finite. You don't get the language inside the infinite domain, right? So domain has infinite languages, you take infinite, but when you do the finite subset, you don't get infinite. So this is not closed. Except this, The finite subset means result is always finite. When the result is always finite, it satisfies everybody. Okay. Inverse homomorphism, it's closed for all the domains. Inverse homomorphism. So make the table for everyone. Now we are talking about CFLs and DCFLs. Can I choose option A? CFLs and DCFLs, this finite subset is closed. What about inverse homomorphism? Is closed for regulars, DCFLs, CFLs. So it is also. And a prefix is closed for, yes, the prefix is closed for DCFL, and already we know it's closed for CFL, even it is closed for regular. But suffix, if I ask, suffix is not closed for DCFL. Suffix and substring will not, but prefix is closed for DCFL. But these three are going to be closed for CFLs, also closed for DCFLs, and also closed for regular languages. But finite languages, infinite languages, you need to do extra work. Okay, with this, we have completed the closure properties of regulars, DCFLs, CFLs, and many. So I want you to think about a very simple table, and make the table yourself. Make the table yourself and try to fill this table. Okay, how many domains we have seen so far? One is the finite, other one is infinite, and other one is regular, DCFL, and then CFL. Okay. So this is the table you have. Okay. Let me make the first one. Just first one, do the union. Second one, intersection. Very, very important, only we will write here. So fill the table and try to keep with you, but this is a homework, so you have to do extra work than my explanation, because many people are interested to do the homework. Complement, and then concatenation. You can go for a difference, you can go for a reversal. I will give only 8, remaining you just do on your own. Subset, 8th, union, intersection, complement, concatenation, difference, reversal, subset, substitution, homomorphism that you do on your own. I think 7 would be sufficient. Concatenation is covered. Yeah. Let me think, any other important operation that is needed. Okay, just I will keep substitution, so that most of the important point will cover. Okay. For this, what you have to do, for this is a domain, right? For finite languages, for finite sets, what happens? Is it closed or not closed? Okay, I'll fill one, even 9th one, in case if you are interested. 9th one also, I'll just keep one, but not extra. Cleany closure. If you know this, cleany star. If you know this, cleany plus also same answer. Cleany plus also same answer. So you can keep yourself. Okay, cleany star, one more. So I can delete this. Okay. For finite sets, I'll just fill it. Union, closed or not closed? Union of two finite languages? Yes. Intersection of two finites? Yes. Complement of finite? No. Maybe, sorry, it's always not finite. Concatenation? Yes. Difference, finite minus finite is always finite. Reversal, so closed or not closed? That's all. 2 points you need to remember. Reversal of finite? Yes. Subset of finite? Yes. Substitution of a finite with a finite language is again finite. Cleany star, finite language, when you do the cleany closure, you may or may not get. So I filled one column, so remaining is your job. Okay. So do not expect me to answer all these questions, but you can catch me and ask any doubt later, not now. For infinite sets, for regular sets, for deterministic context free sets, so DCFLs, for context free languages. You fill this table and keep with you, definitely it will help you for the exam point of view. Okay, one column I have filled, another column if you are interested I will fill it. Yes, take this infinite because many people will feel difficult. As you see, you are studying about this 3, but you do not study much about this anywhere. So, I will fill this infinite closed, intersection of 2 infinite not closed, complement of infinite may or may not be infinite, that means not closed. So, this cross is very dangerous, not closed only I am saying, result I am not saying, result you need to make another table. Is that always gets finite? Yes, always finite, always finite, always. When I put a cross, what is it? It is always not finite or sometimes not finite. You need to cross check. That depends on, cross might refer two things. It might be always outside the domain or it might be sometimes only outside the domain. So, you need to identify the difference. Okay. Concatenation of 2 infinite is always infinite. Difference, infinite minus infinite could happen anything. Reversal of infinite is always infinite, and subset of infinite may or may not be infinite. Substitution of infinite with infinite language, always infinite. Clinic closure of infinite, always infinite. So, I hope you got my point how to answer these questions. These things I already answered, but except clinic star I did not explain for others, but you think about it. I will just explain here. Clinic closure I am explaining as it is not explained for all the domains. Clinic closure of regular is regular. Clinic closure of DCFL need not be DCFL, that is why I put a cross mark. Clinic closure of CFL is always CFL. Okay. So, remaining just take care of it. First you should know the definition of each operation, then you should know whether you have an algorithm or not. If you do not have an algorithm, find the counter example which goes outside the domain that you take for the particular column. Okay. So, I am giving this is homework for you. Okay. Fill this. Okay. With this summary, you have understood very important operations like what happens to union, intersection. These are all what the closure properties, L power reverse, L star and subset operation, right. All these operations you have learned for various domains, and definitely it is going to be at least one question in every year. So, that is why closure properties is a very special topic. After understanding all the languages, you should come to the closure properties to do the operations over your domain. Okay. Thank you so much. In case if you have any doubts, I am here always to help you, and do not forget to like this video, and also do not forget to ask your doubts in below the comment section. I am happy to help you. Thank you so much. Take care. See you. Bye bye. I will meet you in the next coming lecture, that is the Turing motion and undecidability.